Welcome back to this machine learning case study. Today we're going to cover the paper titled The Optimization of Biomass Production Forecasting via Machine Learning Techniques. So, forests help regulate climate change through carbon storage in extensive vegetation like forests, where the biomass can then be used as a carbon neutral energy source. However, in order to create a balance in which carbon dioxide linked climate change is mitigated while producing the renewable energy source, forest biomass production needs to be managed and monitored in a very strategic manner. Unfortunately, traditional biomass estimation techniques like direct measurement are costly, time consuming, and very labor intensive. The goal of this study was to use machine learning to enhance the precision of predictions in the estimation of biomass production, including above ground biomass, which are the branches, leaves, and trunk, the below ground biomass, which is the roots of the tree, and then the total biomass yield. The machine learning algorithms used to do this were the Gaussian processes, kernel ridge regression, and extreme learning machine algorithms. The authors used a dataset consisting of 175 destructively sampled trees from 27 plots in the central highlands of Vietnam. Input variables included soil type, forest type, tree height, diameter at breast height, and annual temperature. And the data set was split, 75% of it going toward training of the model and 20% going toward testing of the model. So initially, all models were used to predict the total biomass yield. And this model evaluation showed that the Gaussian processes algorithm yielded the most accurate and reliable results with the minimum error values and highest performance values, as shown in this table here. Moving on to the second step, the Gaussian process model was then used to predict the above ground biomass and below ground biomass yields. The model was found to have efficient prediction capability with consistently high R squared values and explained variance values. This affirms the robustness and generalizability of the Gaussian processes model in prediction across every biomass category, including above ground biomass, below ground biomass, and total biomass yield. So to conclude, the biomass prediction through the Gaussian processes algorithm is fast, cost-effective, and extremely accurate, which helps support more sustainable resource allocation, guide land use decisions, and enhance carbon balance models. However, this does come with some limitations. The region-specific nature of the data may limit the model's applicability to different geographical or climatic circumstances. And real-time or large-scale applications may encounter difficulties due to the Gaussian processes model's computational complexity. If you're curious to learn more, you can read the paper at this full citation. Thank you for watching.